Okay, on to QOD number 38. And so we're going to continue we're going to start talking about pHs and stuff like that. And so in order to do that, we just need to define what the P function is. And that is that the P of X is equal to the negative base 10 log of X. I'd mentioned back in the previous two chapters that most of what we do in this class with logarithms is natural logarithms, but the one exception to that is the P function. And the most common use of it is in pH. But you just need to remember that the P of X, the P function is the P of X is equal to the negative log of X. And so therefore we can move right on to pH, which is defined as the negative log of the H plus concentration, or as it's written here, the negative log of the hydronium ion concentration. And so we can talk about, and so you will see it written both ways. And as I said before in class, you need to be able to just kind of view the hydronium and H plus as being interchangeable. And so the pH is a measurement of acidity, and it's defined as the negative log of the H plus concentration. So we can take some examples. If the hydronium ion concentration of a solution is equal to 1, then the pH is equal to 0, because the base 10 log of 1 is 0, and negative 0, of course, is 0. And so if I've got a 1 molar solution, it has a pH of 0. If I have a 0.1 molar solution, that's 10 to the minus 1. The log is negative 1. The negative log is 1. If I have a 0.01 molar solution, the pH is going to be 2. If I've got a 0.001 molar solution, which is 10 to the minus 3 molar, the pH is going to be 3, etc. One thing to take away from this is to understand that every pH unit is a logarithmic unit. So every time you go up by 1 unit of pH, you're going up or down by a 10-fold concentration of hydronium ions or H plus ions. Okay, so we can try some just simple pH problems. And so these are the sorts of things where you can pause the video if you want, work out the calculator, and then turn it back on. Question, what is the pH of a solution whose hydronium ion concentration is equal to 10 to the minus 10th? Answer, that is 10. That's very easy because there's no coefficient in your scientific notation here. It's just 1 times 10 to the minus 10th, and so therefore that is 10. Now I'll give you one that's a little bit, actually requires the use of a calculator. What is the pH of a solution whose hydronium ion concentration is equal to 1.8 times 10 to the minus 5th? Well, to answer that, you now just need to punch into your calculator negative log and then 1.8 e negative 5. And when you do that, you get 4.74. So the log of 1.8 times 10 to the minus 5th is negative 4.74. Therefore, the pH is equal to 4.74. So that's how you calculate pH if you know the hydronium ion concentration. Okay, from there we're going to whiz on and talk about what's called the autoionization of water. Even in a completely pure sample of water, there are some ions present because water, to a very small degree, will react with itself to ionize. So as we've seen, water is amphoteric, which means it can act as both an acid and a base. And it can react with itself, in which one water molecule acts as the acid and one water molecule acts as the base. So in pure water, a tiny fraction of those molecules are going to undergo that acid-base reaction, and we call that autoionization. And so, again, to talk about what we're talking about, it is a molecule of water acting as an acid, reacting with a molecule of water that acts as a base. This one's going to donate a proton, and therefore it becomes hydroxide because it gave up a proton. This one is going to accept a proton, therefore it becomes hydronium because it accepted a proton. Of course, the other way to write this is just to leave out one of the water molecules and think of it, instead of 2 water molecules reacting, which is actually what's happening, just 1 water molecule ionizing into H plus OH minus. So you're welcome to sort of consider this occurring in either one of these ways. Well, this is an equilibrium reaction, right? We've got an equilibrium arrow. This is an equilibrium reaction, and it's governed by an equilibrium constant. This doesn't happen very much, so you can imagine that the magnitude of the equilibrium constant is very small. And in fact, and so we can write an equilibrium constant expression for this. Whether or not we're including waters, back up, whether or not we're considering this reaction or this reaction, once again, because this is occurring in aqueous solution, we're not going to include water in the equilibrium constant expression. So we would simply write the equilibrium constant expression either like this, in which we're designating as the cation as hydronium, or like this, in which we're designating the cation simply as H+. This specific Kc has a special name. It's called Kw. It is the ion product constant for water. And so this particular expression is what's called the Kw expression. I think I mentioned back when we first started talking about equilibrium that when it comes to Kc, there are lots of special values of Kc, and this is kind of the first one we're going to encounter. It's Kw, which is the ion constant product for water. And at 25 degrees Celsius, Kw is equal to 1 times 10 to the minus 14. And so that's pretty much the only value for Kw that we're ever going to use. We're always going to consider these things under standard state conditions. And so at 25 degrees Celsius, Kw is 10 to the minus 14. Well, that raises the question of how do we determine the pH of pure water? And so if you think about so first of all, in any aqueous system, whether it's neutral or acidic or basic, Kw is going to be equal to the hydronium ion concentration times the hydroxide concentration, which is going to be equal to 10 to the minus 14. In pure water, because I haven't added any additional hydronium or hydroxide to it, these two species are forming at the same rate, right? It takes every time two water molecules react with each other, I get one hydronium and one hydroxide. That means that in pure water, in which I haven't added any acid or base to it, the hydronium ion concentration is going to be equal to the hydroxide ion concentration. So I can therefore just, since hydroxide is equal to hydronium, I can substitute hydronium in for hydroxide. So in neutral water, Kw is equal to hydronium squared, right? Because as long as these two are equal to each other, I can substitute one for the other. Therefore, the hydronium ion concentration is going to be equal to the square root of Kw, and that is 1 times 10 to the minus 7. Well, once we know that the hydronium ion concentration in pure water is 1 times 10 to the minus 7, we can take the negative log of that, and that is equal to 7. And so if you're wondering why it is that 7 has been defined as the pH of a neutral solution, that's because in a neutral solution, the H plus concentration is equal to the OH minus concentration. Therefore, H plus squared is equal to 10 to the minus 14th. Therefore, H plus is equal to 10 to the minus 7. Therefore, the pH is equal to 7. If it is an acidic solution, it's going to have a hydronium ion concentration that is greater than pure water, and therefore it's going to have a pH that is less than 7. If it's a basic solution, it's going to have more hydroxide and less hydronium than pure water. Remember, the hydronium and hydroxide concentrations are inversely proportional to each other because they always have to multiply out to 10 to the minus 14. So if the hydronium ion goes up, the hydroxide ion goes down. If the hydroxide ion goes up, the hydronium ion goes down. So in a base which has a high hydroxide concentration, the hydronium is going to be less than 10 to the minus 7, and therefore it's going to have a pH greater than 7. And so this is just in tabulated form. For an acidic solution, the H plus concentration is greater than 10 to the minus 7. The hydroxide concentration is less than 10 to the minus 7. The negative log of this is going to be less than 7. Under neutral conditions, they're equal and the pH is 7. Under basic conditions, the H plus is less than 10 to the minus 17th. Therefore, the pH is going to be, less than 10 to the minus 7th. And therefore, the pH is going to be greater than 7. Okay, we can also define the POH function. Your book talks about this, although I don't think the College Board much cares for POH. I've been looking through some old exams and haven't seen any examples in which you need to know how to calculate or define POH. But just in case I'm wrong, we're going to do this quickly in one slide. Because it's the same P function, because again, we're using a P function, it's simply defined that POH is the negative log of the hydroxide concentration. So if we consider a solution whose hydronium ion concentration is 10 to the minus fifth, its hydroxide ion concentration is going to be 10 to the minus ninth, right? Because hydronium concentration times hydroxide concentration has to be equal to 10 to the minus 14. So if it's got a hydronium ion concentration of 10 to the minus fifth, it's got a hydroxide concentration of 10 to the minus ninth. Its pH is the negative log of its hydronium concentration, which is 5. Its POH is the negative log of its hydroxide concentration, which is equal to 9. And what you'll find out if you play with this at all is that for any aqueous solution, its pH plus its POH is going to be equal to 14. In this case, if the pH is 5, the POH is 9. If the pH was 10, the POH would be 4. If the pH is 6.5, the POH is going to be 7.5. Okay, let's move on to something else new, strong acids. You'll remember back in chapter 4, we're actually going to start getting into some quantitative stuff. Well, we already have with calculating some P function stuff, but now we're going to get into some ice table stuff in just a second. Back in chapter 4, we memorized 7 strong acids, and every other acid is either a weak acid or a negligible acid. And so just as a reminder, these are the 7 strong acids: HCl, HBr, HI, nitric, sulfuric, chloric, and perchloric. Every other acid is either a weak acid or a negligible acid. Now remember, by definition, strong acids are going to ionize completely in aqueous solution. And that means that for the 6 out of the 7 of these that are monoprotic, the only one that's diprotic is sulfuric acid. And we'll talk about how much it ionizes at another time. But for the other 6, which are all monoprotic, the hydronium ion concentration at equilibrium is going to be equal to the acid concentration. In other words, if I make a 1 molar solution of HCl, I've got a 1 molar solution of H+. If I make a 0.5 molar solution of nitric acid, I've got a 0.5 molar solution of H+. The hydronium ion concentration or the hydrogen ion concentration is going to be equal to the acid concentration because it ionizes completely. We also learned back in chapter 4 that there are strong bases, a series of strong bases. They are all of the alkali metal hydroxides and these 3 group 2 hydroxides, calcium, strontium, and barium. Again, these are water soluble, and so they're going to dissociate completely in aqueous solution. And therefore, for any alkali metal hydroxide, sodium hydroxide, lithium hydroxide, potassium hydroxide, the hydroxide concentration is going to be equal to the concentration of the compound because it will have ionized, dissociated completely. For group 2 metal hydroxides, the hydroxide concentration is going to be 2 times the compound concentration. If I have a 1 molar solution of strontium hydroxide, it's actually 2 molar in hydroxide, right? Because there's 2 hydroxides per mole. If I've got a 0.4 molar solution of barium hydroxide, I've got a 0.8 molar solution of hydroxide. So we can try some problems. What is the pH of a 0.02 molar solution of HBr? HBr is a strong acid. Therefore, the hydrogen ion concentration is equal to the HBr concentration, which is equal to 0.02. Therefore, the pH is equal to the negative log of 0.02, which is 1.7. We can also use the same methods that we've talked about to calculate the pH of a base solution. So what is the pH of a 10 to the minus 1 molar solution of KOH? That is a 0.1 molar solution of KOH. Well, if the hydroxide solution is equal to the KOH, the hydroxide concentration is equal to the KOH concentration, which is equal to 10 to the minus 1. We use Kw again to get the hydronium ion concentration. It's going to be Kw divided by the hydroxide ion concentration, which is equal to 10 to the minus 13. And that makes sense because 10 to the minus 1 times 10 to the minus 13 is equal to Kw, 10 to the minus 14. Therefore, the pH is equal to the negative log of 10 to the minus 13, which is 13. Okay, now we're going to do some ice table stuff. And to do that, we have to define the acid ion. I don't actually like the term dissociation constant, and I wish I had actually changed this before I wrote this, before I started the recording. I refer to this as an acid ionization constant, because it's actually ionizing, not dissociating. But we can write a generalized acid ionization reaction this way, in which we call our generic acid HA. When it ionizes, it gives us hydronium plus A minus. And so we can write the equilibrium constant expression for that. Once more, we're going to leave the water out because it is the solvent. It is not only a reactant, it's also the solvent. Therefore, either one of these would be an acceptable equilibrium constant expression for this reaction. Kc is equal to product concentrations, H3O plus times A minus, or H plus times A minus, over reactant concentration, which is HA, but not the water. And we define this as Ka. So we've now defined some special subsets of Kc. We talked earlier about Kw. Now, this acid ionization constant is called Ka. And so each acid, whether it's strong or weak, has a unique value for Ka. And so this is a group of weak acids, but now you can see that they're not all equally weak. And in a previous table, you saw that they were actually rank ordered by strength. But we didn't explain to you how we rank order them by strength. Now we can say we're rank ordering them by the value of their Ka. And so the higher the Ka, the stronger the acid. The smaller the Ka, the weaker the acid. So you can see that weak acids span actually a very large territory when it comes to values for Ka. And so these are stronger because their Ka values are larger. These are weaker because their Ka values are smaller. We can calculate a Ka in a very clever method by making a solution of a known concentration of a particular acid and then measuring its pH. So here's a problem we're going to do. I make a 0.1 molar solution of formic acid, which has this formula, HCOOH. This hydrogen here, this acidic hydrogen. And at 25 degrees Celsius, its pH is 2.38. Calculate the value of Ka for formic acid at this temperature. Well, this is an ice table problem, and it's like some ice table problems that we did back in chapter 15, in which we know the initial concentrations of reactants and products, and we know the equilibrium concentration of one of the products via pH. So let me explain to you how we do that, and then walk through the ice table calculation. And we have this equilibrium constant expression we can apply. Once we get these numbers, we can plug them into the Ka expression. So this is the Ka expression for formic acid. Okay. To calculate Ka, we need to have the equilibrium concentrations of all three things: the formic acid, the formate ion that's formed when it ionizes, and the H plus that's formed when it ionizes. Well, remember that H plus and formate are forming together stoichiometrically, and so therefore, if we know the pH, we can find the hydronium ion concentration. If we know the hydronium ion concentration, we also know the formate concentration, because these are forming at the same rate because they have the same coefficient in the balanced equation. So we can figure out what the equilibrium concentration of hydronium is because we know the pH. So the pH is equal to the negative log of the H plus, which is equal to 2.38. Therefore, the log of the H plus is equal to negative 2.38. Therefore, the hydronium concentration is 10 to the negative 2.38. which is equal to 4.2 times 10 to the minus 3. And we know from the balanced equation that the formate concentration is going to be equal to the hydronium concentration, and therefore it's also 4.2 times 10 to the minus. So let's go to the ICE table. We had the initial concentration of formic acid was given as 0.1. Before any ionization has occurred and equilibrium has been reached, the hydronium and the formate concentrations are 0. We know now from measuring the pH that the concentration of both hydronium and formate at equilibrium is 4.2 times 10 to the minus 3. Therefore, we know that our X is equal to 4.2 times 10 to the minus 3. The products are forming the change in concentration of the products to get as we reach equilibrium is plus 4.2 times 10 to the minus 3. The change in concentration of the reactant as we reach equilibrium is minus 4.2 times 10 to the minus 3. At equilibrium, it's 0.1 minus 0.0042, which is basically, when it comes to sig figs, that's basically when you round that to the 2 sig figs you started with, the 2 decimal places you started with, you're back to 0.10. And so actually the change in concentration of the acid is insignificant compared to its initial concentration. We have the equilibrium constant expression. We can plug those values into the Ka expression, and we get the value of Ka for formic acid being 1.8 times 10 to the minus 4. We can also calculate one more thing, which is called percent ionization in this case, which simply means to what extent did the reaction occur, to what percent did the reaction occur. That's going to be defined by the concentration of the product, hydronium, over the concentration of the reactant, the weak acid, times 100%. In this case, the hydronium concentration at equilibrium was 4.2 times 10 to the minus 3. The formic acid concentration initially was 0.1. When I divide one by the other and multiply by 100, I get a 4.2% ionization. And I've been saying over the course of the year that weak acids tend to ionize on the order of like between 1 and 5%. It depends both on the Ka of the acid and also the initial concentration of the acid, as we'll see as we move through this chapter. Okay, I've been sprinting to the end of this video. What kind of a thing can you expect to get on a QOD? I would certainly expect you to be able, using a calculator, to calculate pH from H+ concentration or vice versa. And also just to be able to understand some of the basics about P functions, what the expression for HA means, what the KW expression means, things like that. So be sure to do some of the suggested end of chapter problems, and we will see you in class, and thanks for watching.